Right. So I quickly go on what we have seen last week. There is one small result which I like. It says that for any two-dimensional, this is a two-dimensional connected means in one part, compact. Compact here means simply you can put it in a box. It's not infinity, so it's in a box. I didn't define orientable. I will come back to it, but it means you can walk on this surface and come back with the same orientation. I will be more precise later. But all these two-dimensional connected compact orientable manifolds are in fact sphere plus handles attached on it, all of them. So this is a result for manifolds in 2 dimensions, compact manifold in 2 dimensions. Then I just wanted to emphasize, a manifold at around every P, we can find a neighborhood which is homomorphic to an open set in Rn. We call this pair an open set on this map going from the manifold to Rn, either a chart or it's also called a coordinate neighborhood or a coordinate system. So these 3 expressions will be used. Now we have also introduced topological manifold with boundary. If you cut this into an upper part and a lower part, you would have a boundary like on this picture. And how we define a topological manifold with boundary, we have 2 kinds of open set, either a set which is homomorphic to an open set of Rn, or which is homomorphic to what I call Hn, which is a half plane. So it's only the upper part of this plane, and you have a boundary. So this part, the boundary, what we call the boundary, should be related to this part. There is a precise definition in the notes. Right. Then this is all about topological manifolds, but then we need to go through smooth manifolds. So smooth manifold is a topological manifold, but in addition, you have what is called a maximal atlas. Think about what you know as an atlas. It means a family of charts, so family of maps, one open set, one function from this open set to a subset of Rn. But such that when you have 2 charts with an intersection, then you can compose this function, because it's bijective, you can go back. Starting here, you can go and arrive here, and then go up to here. Then you are from part of Rn to part of Rn. This map has to be smooth in the sense of function from Rn to Rn. And the same for the reverse map. If you start here, you end up here, and then you compose with phi, you arrive here. This has to be smooth. And you do this for all charts. And this gives you a maximal atlas. We say that it has smooth transition function. So this is a smooth manifold. You can describe it with smooth function like this. Then when you have 2 manifolds, 2 smooth manifolds, M and N, by the way, I will always use this one is always of dimension M. This one is always of dimension N. A smooth manifold is a map from one manifold M to a manifold N. And how do you express the notion of smoothness? The same here, you can always map these 2 parts of Rm, precisely. Here you can always map these 2 parts of Rn. And then if you do the composition of this inverse map, because it's going in this direction. So this inverse map, then this one arriving here, and then this one, you are from Rm to Rn, and there is a meaning for smooth. And it means, since we have smooth map, we can just, what is a diffeomorphism? It's when it's smooth in one direction, it's bijective and smooth with the inverse also smooth. So it's when the inverse, it's bijective and the inverse is also smooth. But even if it goes only in one direction, you can define the Jacobian because you have a function from Rm to Rn, which is differentiable. So the Jacobian matrix is meaningful and it gives you a matrix and you can look at its rank. And we call it the rank at one point P. So we code it at point P, but in fact, we have to take the image phi of P, and then we do the composition, we compute the Jacobian matrix, and we check what is its rank. Now, if this rank is independent of the local chart you choose because of this property, you don't change the rank if you change the local chart. On the other hand, this Jacobian matrix, its rank can be a function of P. If you move to a different P, and I gave you an example in one dimension, if you go to a different P, maybe the rank is different. Now, just for information, we called immersion when the rank of F is constant and equal to the dimension of this, of this manifold, and we call submersion when still the rank is constant, so it's independent of P, but it's equal to this. Of course, the dimension cannot be bigger than M or N. If you think about it, you have a matrix M times N, so the rank is at most these two numbers. Now, if we have a immersion, and I finished last week on this, if we have an immersion, a picture is you take the real line and you send it to the plane like this. This is an immersion as long as the rank is constant. So you do not stop at one point, but suppose we don't stop on this curve. This is an immersion. It can or it cannot be injective. This example is not injective because we go 2 times through the same point, but we can also have something which is injective. So if we have an injective immersion, so we have the one-dimensional line sent on part of R2, of course, we can put the topology of the line on this curve. So I can just consider all open sets, and open sets are typically intervals, and I just reproduce the intervals here. This gives me a topology on this simply because it's a nice function from this one to this one. However, it's not really interesting because you don't use anything about the fact that it's in R2. It's only one dimension on one dimension. So there is a new notion which I will introduce because we can have something as, let me do a third picture, something as this, I mentioned last week, or something as, you know, just going to a, like a spiral. So this make, if you just look at the topology inherited from this line to this, you don't really see the difference between both as long as it is injective. But of course, as a subset of R2, it's very different than this line. And this is the next notion I'm going to introduce. Do you have any question or remark? Today, the first part is rather nice. The second part is the first abstract part, but it should be fine. Let's see. It's about the tangent space. So let me discuss a little bit about this, and I already mentioned last week. Now, if we look at this with the subspace topology of R2, so the open set in R2 are balls, and in particular, if I draw a ball like this, okay, let me do it more closely. So we are approaching, but never reaching the other curve. So when we go to infinity here, we are simply approaching this part. If we look at the subspace topology, so the topology that we get from balls in R2, we can see that an open set with the subspace topology is like this plus like this. And this is quite different from open set in this. Or the same in this example, if I take the subspace topology from R2, I would get this as an open set, which is quite different again from one interval there. So there is a notion for this, but first let me make a remark. So I just continue with this. So I mean, this setting F is injective immersion. So a picture like this one or these two pictures. So when F is an injective immersion, so we think about, we just represent in a different space. If F of M, so the image, what we see, is endowed. So let me write it. This is a subset of N because F is from M to N. F of M inside N is endowed with the subspace topology precisely inherited, so that we inherited from N. So this is the two pictures I mentioned there. This topology might not coincide with the topology coming from M. So this is what I try to explain with this picture. If I just take the topology from M and send it on any of these curves, I would have something quite boring. I just transform an open set into this. Now, if I take the subspace topology that I get by R2, I have something different. It depends. But there is one notion in order to make a difference between these two situations. And this is the next definition. So what is the definition in order to make a difference between these two things? That let F, again, from M to smooth manifolds, from M to N, be an injective immersion. Immersion, you should think about it. We don't lose anything when we send it to the new space. Then F is an embedding. This is a new word, embedding, or it's also called embedding, depending on the author. Embedding or embedding. Embedding or embedding if F is a homeomorphism between, so I will explain, of course, between M and F of M when F of M is endowed with the subspace topology precisely. From N. As I said, I want to make the difference between these pictures. Which one is an embedding? Can you, if you look at, we have 4 pictures. 1, 2, let's say 3, 4. Which one would correspond to embedding or embedding according to this definition? Somebody said 1? Okay. Somebody, another number. So what we want to consider F. No, sorry, first we consider M. This is M. and the image. So we have different image by F. First, we want it to be injective. So it already eliminates one option because the second one is not injective. I already mentioned, so cannot be two. And now we want to say that F is a homeomorphism, something both continuous when between M and its image, when the image has a topology, which is called the subspace topology given by N. So precisely, I mentioned on these two cases, they are not, because the open set here or the open set here given by the subspace topology, so by open set of R2, do not look like open set here. So the only one which satisfies that it is an immersion is this one. But this one, not with the initial topology, but with the one, they look quite similar, but with the one that you obtain when you take intersection with balls of R2. Yes?
What you could have taken points, and then the new topology is not injected from the open sets.
Say it again, I cannot understand. On M. The topology on, the topology here.
Yeah, you can take a point, U equals to a point, and then take the subspace.
No, but a point is not an open set. A
Yes.
point is not an open set of R2.
But then you have to take open set to be a subspace topology.
No, the subspace topology, by definition, you take open set of the big space N and take its intersection with your, what you consider here, this curve. So I take, typically an open set in R2 is a ball. Of course, we have other, but this is the basis. So we take a ball, we take the intersection with the curve, I end up with an interval like this, and there are isomorphism between these two things. So no, this is an embedding. So an embedding means you represent something in a bigger space, but you respect the local structure. No, it's not the local. You respect the global structure, because even though it looks something local, in fact, if you look carefully, the problem is a global one. In fact, I will write a remark, and if somebody wants to understand this remark and write something on it, I would be very happy, but I will not spend too much time on it. Just finish the definition. In this case, we call then f of m, if we are in this situation, is called an embedded submanifold. Embedded submanifold. So the way you should think about it is we put our initial manifold M into N, probably something bigger, but we take care that we don't have this kind of problem. So the topology, the subspace topology on the curve or on the image is quite similar to the initial topology. Yes? This, no, this is an N. You take, because you want to take the topology from the bigger space, which is N. F is from M to N.
So everything is like the other side. So when you compare like the first.
Okay. Wait. We compare M on its image. M has the initial topology, and I'm specifying, or I emphasize that this one is with the subspace topology. So I compare M with its initial topology with its image with the subspace topology. And what is the remark I wanted to say? So it's a remark, if somebody wants to think about it. This property, so embedding is a global property. It's a global property because it is always true locally. I am not going to say more about this. Okay, this is something you can think about. So it's really something global that you have to study. If you just look at a small piece and just look at a small piece, small enough, you don't face this kind of problem. Now there is something which saves us for many situations. If you look at the definition of a smooth manifold, it's not easy. While if I show you this, you wouldn't be surprised that this is a smooth manifold without the complicated definition. And why you have the feeling that this is a smooth manifold, it's because of what I'm going to write now, which is in fact also related to this. So let me just define a small thing for epsilon. I want to define an open box. For epsilon bigger than 0, we set C n epsilon of 0. I want a box and not a ball. So this is a set of x1, x2, up to xn inside Rn. So we are in n dimension. And how do I define a box? How do I define a box? I need that centered at 0. It's a box centered at 0. I need the xj to be smaller equal to be strictly smaller than epsilon for j equal to 1 up to n. Think about it already in one dimension, it makes an open interval. And in 2 dimensions, it makes an open square. So the square without the boundary of size or of length 2 epsilon. Think about it. This is a definition of an open box centered at 0. At 0 inside Rn. I will just need it. So I need a box and not a ball. Okay. Now, let me explain let me write why we can easily feel what is a smooth manifold. Because of the following property. A subset of a smooth manifold, N. And I encourage you for this statement to think about N is simply Rn. Of course, it's slightly more general, but if you have Rn in mind, it's sufficient. So a subset of Rn has what we call it's a definition, the M submanifold properties. And I will do an example with my balloon. It has a M submanifold property if, look, sorry, a subset M, I should give a name. A subset M of a smooth manifold has a M submanifold property if for any P belonging to M, there exists a chart U phi, a chart, but so far I spoke only about one manifold. The other one is just a set, so this can be only a chart of N. A chart of N with P inside U, such that we have three properties. So let me try to make a picture. I will consider N is R3. This is N, I identify it with R3. And I take a subset. And this subset is going to be like this paper in R3. And I take a point U, P inside. And now the statement says it has a, in this case, it will be the two submanifold property. In this example, if for any P, you can find a chart in N. So what is typically a chart in N is a ball, because in R3, open set are typically ball. So if you can find a ball U and a map from this U to a certain box in R3, be careful my picture. Oh, I can do it in R3. This is a box in R3. Okay, maybe it's not a good box, but okay, you can see it. So if for any P you can find a chart of N, so open ball, and phi going to this open ball to Rn, but in my pictures is R3, such that we have three properties. Phi of P is equal to the zero of Rn. So it means this P is sent to 0. The second point is that the image of U is precisely this Cn epsilon of 0. So this U, this ball, is sent on this box. It's on purpose. And what is the third property, which is probably the most important, is that, look, so in these two lines, the M did not play any role. M did not play any role, but what is the third one? If I take phi of U intersection with M, so now M plays a role. Think about it. U is something in 3 dimensions. Intersection with, on this picture, M is 2 dimensions. So the intersection is going to be intersection of the ball and of the surface. It's going to be something on the surface, right? So phi of this intersection can be written as x1, x2, xm, and then 0, 0 up to xn inside Rn. Inside, in fact, it is inside Cn epsilon of 0 because it's inside M. That's it. So what does it mean? It means, so this is in R3. N is R3. This is a surface. This is my M. I take a point P. I put a box, or an open set of R3 around this P. Now, this open set of R3 around P and phi should have the property that first, the point P is sent to 0. Then this ball is sent to this open cube. This is always possible. But the last thing is that the intersection of the ball in R3 plus my manifold, this is this intersection, is sent on the floor of this cube. So we have a cube in R3. You take only a subspace 2 dimension. On this picture, it would be 1, 2, and then 0. So you can it's really, you can map this to something of lower dimension in Rn. So this is a very strong constraint, but it's quite clear. Locally, you can transform this, the small piece of this surface, to something on the floor. This is a this definition. Yes. Thank you. Yes, the last one is 0. Yeah. I wanted to write this is the m+1 entry until the nth entry or coordinate. You're right. Thank you. So you have some dimension are just 0. This is why m is smaller or equal to n. And this chart has a name. This chart, so it's still in the definition, is called the preferred coordinates with respect to m. It's because you can locally, you can transform your manifold, which is something in R3, but you can locally look at it as something that you put on the floor. And you can guess now why. So this is definition, but it's rather easy to apply it. And the lemma, or the important result after this, is that with this construction, so if M inside N has this M submanifold property, then M can be or is or becomes, let's see, then M becomes a smooth manifold with the subspace topology from N. So you take the subspace topology, but you need to do something. What you need to do, you need to forget the 0 because you want to have a m-dimensional manifold. So it's not only you take the subspace topology, but you also forget what is not necessary. So what you need to do is you take a projection, in fact, on the m first coordinate. So n and all preferred coordinates defined. So far, it's only a topological space, a topological manifold. But now, by using the preferred coordinates, they define a smooth structure. So you have the differentiability, or a smooth atlas. I can write a smooth atlas. Smooth atlas once restricted to the first m coordinate. So I forget the 0. This is the trick. So if, as I said, this is very useful because start with this. Locally, you can easily realize that you can send a small part to 0 with the construction. And once you put everything together, it becomes a smooth manifold. What is the the negative part of this is this manifold it becomes a manifold only because you look at something bigger. So you need an ambient space. You need something around it, and you get it as a manifold because it's a restriction of something bigger. Okay. So if it's useful for many manifolds, this is the approach. But if you want to have a manifold which is not inside something bigger, it's not the right approach. I mean, it's not what we need. Okay, and such manifolds have a name. So these manifolds, so when you obtain them like this, are called regular submanifold. Regular submanifold. And in fact, most of the pictures are of this type because we are always living in R3 and looking at something of lower dimension. So most of the time, the pictures I show you are exactly in this setting. So that's why it's useful. All right. Any question or any remark? So we have seen two things. What is embedding? When you put a certain manifold in another one, but you respect some properties, some global properties. And the other one is how we can find out that this is a smooth manifold by looking that it has good properties when you look at it inside R3. Yes?
So there are special reasons why we need to define it in a box of.
No, it's look because you make nice pictures. That's it. You can no, but boxes are nice because you can indeed take only a few coordinates and you obtain a plane. I mean, you have a hyperplane. So it's very convenient. But, you know, a sphere and a box, topologically, this is the same. You can deform a box, an open box. You can just transform it into a sphere. So there is no big difference. It's just convenient. Okay, so with this, we finished chapter 1. Yes? No. So you remember it's no more written, but U is an open set in R3 on this picture. So when I take the intersection of the ball, you know, you have a, okay, I cannot do it with this because I cannot open it, but take this is a ball in R3 and I intersect it with the surface M. So what we obtain is a kind of circle on this surface. It's not a circle, but no. Or in fact, it's not a circle. I should say it's a disk. Because it's not only the outside part, it's really the disk that you obtain. In R3, this is it's a sphere. I should speak about sphere. This U in R3 is a sphere. It contains the interior. And then I take its intersection with this plane, and I obtain a kind of disk. And this disk is transformed into a square. All right. This is what is called regular manifolds. And as I said, in most of the pictures, this is what we see. Okay, now I want to define two new objects. This is chapter 2, which are called the tangent space and what is called a vector field. So probably in calculus 2, you have heard about these two things. We will make them more general. So the first part is 2.1. It's about tangent space. So if you had a good course of calculus, you should have seen an umbrella, calculus 2. This is a surface. It's a parametric surface, so you can obtain it as a function from R2 to R3. And you can draw curves or yeah, curves on this surface. So we have a couple of curves. Here they intersect, this green and the blue one. And how do we get the tangent plane? We take this curve on the surface, we take derivative. The derivative is going to be a tangent vector. And so we have a vector which is just on the surface. And if we take the blue one, we have another vector which is just on the surface. And they generate a plane because two vectors generate a plane. And this plane is what is called the tangent plane. So it's a plane, tangent plane exactly at this point. This is how we define tangent plane in calculus 2. Take a parametric surface, take two curves on it. Of course, these two curves should intersect in a good way. They should not be tangent. But if they intersect like this, take the derivative at this point. You have two vectors, and these two vectors generate a plane. Okay? So this is how we define tangent plane in calculus 2. I will probably recall it if you haven't seen it. So from calculus 2, if M, my umbrella, is a parametric surface, If I consider P a point in M, and a curve is defined by a map from a small interval, epsilon minus epsilon to epsilon to M, with C at 0 is the point P, it's the intersection, then the derivative of this curve is tangent to the surface. Then C prime at 0, which is d over dt of C of t, that you take then at t is equal to 0, is tangent. To the surface at P. And if you take a different curve, you get a different vector, and these two vectors generate a plane with a second curve, and with a second curve, and a second plane, and a second vector, tangent vector, second tangent vector. We get tangent plane. In good situations, of course. But you know, this construction is valid only because we have this manifold in R3. It's not intrinsic. You need to beat this because otherwise you don't give a meaning to this. You need that this surface is really in R3 because the tangent vectors are not on the manifold. They are just above the manifold. So this construction is good if you have an ambient space, but I want to avoid it. I want definitions which are intrinsic. Okay. So I need to define what is a tangent space for a manifold without speaking of an ambient space. But it means it's going to be an abstract definition because I don't have such a nice picture, right? So I need first to define something. So for P belonging to M, this is a smooth, just a smooth manifold. We set C infinity of P. That's a bit surprising as a notation. What is it? This is I will explain the equivalence class of function, of smooth function, on M defined on a neighborhood of. Let me just make a picture before I explain. If I take the line, if the manifold is the line, I choose a P. I want function defined on a neighborhood of P, so on an open set. And these are just smooth functions defined on M. On this small, the interval is arbitrary. So for different function, you may take a different function. And why equivalence class? Why I don't take equivalence classes? Why? Because what I want to identify, look, this red one and this white one, I want to identify them. Why I can identify them? Because on a certain neighborhood of P, they are equal. So as soon as they are two functions are equal on a small set containing P, I just say that they are equal. You know, I'm only interested in what happens essentially at P. So if two functions are equal on a small interval around P, and then they are different, I just count them as one function, one equivalence class. So the set of smooth function or equivalence class of smooth function defined on the neighborhood of P. Now I need to say they are equivalent. So I need to define why they are equivalent if they coincide inside on a smaller neighborhood of P. So as long as two functions are equal just in a small open set containing P, I say that they are in the same equivalence class. So I really want to keep only the information locally around P. So two functions which are different except on a small interval around P, they are in the same equivalence class. They are equal. And observe that this is well defined. What is a smooth function? In fact, I already defined C infinity of Mn. I defined it last week. And I said, or even, last week. And I said if we have C infinity of M with value in R, so the function with taking value in R, I just call this C infinity of M. So these are functions defined on the manifold taking value in R. And the smoothness is, where does it come from? The smoothness is coming from charts. Because why? You have a manifold. I don't know exactly how to represent a function on a manifold. You know, you have your manifold, and at every point, if it is a function with real value, you need to associate one number. So take the temperature at every point on this manifold. This is just one number, and you associate the temperature at every point. So this is a function defined on the manifold, taking value in R, only one component. And it means at every point you have a certain value. And how is it smooth? You remember you have to go through charts. And now you have, when you go with charts, you have, so the function, the temperature, I will call the function F, temperature. And then we have a function from Rn to this, and then F So it's a function from Rn to R. This image is in R. So I can speak about smoothness. So we have defined everything. So we define this for two manifolds. In the case it's only a manifold, we did it. I will use this notation. And now I'm only interested in functions which are defined around P, around one point. Okay, so I need this C infinity of P, the equivalence class of smooth functions defined around P. And they have a name. Elements, it's still in what I'm saying here. Elements of C infinity of P are called germs. This is the official name. Each of them is called a germ. Calculus 1, second course. When you have functions from anything to R, can you define an addition? Can you define the addition of two functions? Yes. Yes, because, okay, let me, so is an algebra. Why? Why can take f and g, two functions in C infinity at P, then you define the sum of f plus g at one point Q. This is f of Q plus g of Q. What is this plus? This is a plus of R. Because this is a number, you can apply that, you can add them. So it's you have an addition. What about multiplication of two functions? The same. You can do it. This is f of Q times g of Q. It's well defined because this is the multiplication of two numbers. So as long as you work with function with value in R, R has an addition and a multiplication. So you can add two functions, multiply two functions, simply because you have the addition. This is the addition of R. And here you have the multiplication of R. It doesn't matter you are on a manifold or on something else. All right? So if you have an addition and a multiplication plus some distributivity, this is called an algebra. If you have just the addition, it would be a vector space. You can also multiply a function by 3. You can multiply by any number. So it's a vector space, but you also have a multiplication. This makes an algebra, which is what we do in calculus 1. We multiply functions, we add functions. Okay? So let's keep it in mind. Any question? Yes.
The condition for finding a tangent is the derivative is 0, but then you can also have a inflection point.
Of course. I said in the good conditions. Yes. You have more. You have some singularities, many things. In the good condition, this is my umbrella. I don't want to do calculus 2 here. I just want to remind a few things. Okay, so we have this feeling, we have a manifold. At every point, we can associate a number. So this is a function from the manifold to R. And whenever you have two functions, you identify them if they are similar at one point. So we are concentrating on everything on a point P. And we can multiply two functions. We can add two functions. What is a tangent space? I told you it's going to be a bit abstract. So definition. If you understand this definition, then you are safe for this semester. The tangent space. Tangent space, and it has a name, it's called TPM. So it's the tangent space TPM of M at P. It consists in the set of all maps, all functions that called xp from C infinity of P to R, satisfying two conditions, satisfying. So really, please be concentrated. A tangent space is going to be a family of functions which take any of these functions here and send them to R. So it takes a function, it sends them to R, and they satisfy two conditions, satisfying for any fg inside this C infinity of P and any alpha beta real numbers, they satisfy two conditions. So what is the first condition? It's linearity. Xp of alpha f plus beta g is alpha xp of f plus beta xp of g. Just let's check that everything is well defined. The left-hand side, I take a function, as I said there, multiply by a number. It's still a function of this type. I can add a second one. We've seen this addition is still an element of CP. So I can apply this guy, which takes such a function and send it to R. On the right-hand side, we just have some numbers. This is a number, this is a number, plus a number, plus a number, times a number. So this is the first condition. This is called the linearity. It's linearity. And the second condition is what is called the Leibniz rule. What is the second condition? Xp of a product. And a product, as we have just seen, is well defined. So I can take the Xp of a product is equal to G xp f plus f of t. This is called Leibniz rule. So far, there is nothing to understand. It's just I'm setting two rules. There is nothing you should try to guess. I'm just giving a definition. We have this family of functions defined around P, and I say that the tangent space is made of maps which take such a function to R and satisfy two conditions. That's it. And in this case, okay, still in the definition, then we can set. Now I want to write what is xp plus yp on the f. So I want to define an addition. So this is I define an addition on this set of functions like this, and the definition is just xp of f plus xp or plus yp of f. The second plus is not the same as the first one. The second one is just an addition of numbers. The first one is my definition. And I want to define also multiplication alpha p evaluated at f. This is alpha xp of f. I put two dot equal because the left-hand side, I define it. On the right-hand side, this is just the multiplication by two numbers. But what do I get when I define this? This makes Tp of M a vector space with its element called vectors. Or called even more precise tangent vectors. All tangent vectors. So please be careful. There is nothing to understand now. It's a definition. I'm fixing some rule. Is there any question about the definition? Please really think about it. XP it's something which take a function and send it to a certain number, and it satisfies two rules. It's like a game. And in a game, you give a set of rules. You cannot play any game without a set of rules, what you are allowed to do. I'm giving you two rules. Yes. This makes TPM a vector space. Oh, vector space. Yes, thank you. Because we have an addition and a multiplication by scalar. Thank you. And the elements are called, its elements are called tangent vectors. That's it. Okay, the definition. So what you want to do now, what happens if I take the simplest manifold Rn? So, but by the way, observe that there is nothing outside of M. It's an intrinsic definition in the sense I don't need anything. I don't need M to be inside something. Okay. Now, what about, let's check what happens if we take M is Rm. I put M. So I want to check what are these guys in this special case. So I take a P inside Rm, point in Rm, and I'm going to fix, we will see, a V, a vector in Rm. So it has M components. I will, from this V, I will define a XP, we will see. For F inside C infinity of Rm, so it's what the pictures I did before. These are just functions defined on a small neighborhood of P. For any functions defined on a point, around a point in Rm, no, sorry, C infinity of P. But P is in Rm. Okay, I'm going to set, I give XP of F, it's sum J from 1 up to M, Bj d over dx jf that should write it. Bj df over dx j t. And probably you remember from calculus 2, it is this. So it's a definition. But you have seen this. How is it called? What is this? Yes, directional derivative. Or derivative in the direction V. Derivative in the direction. Derivative of F in the direction V. Have you have seen this already or not yet? Calculus 2. So this gradient, who has never seen the gradient? You have never seen the gradient? Okay, what is a gradient? The gradient is nothing but It's rather simple. F is a function of n variables. So you have first variable, second variable, third variable. Okay. So you can take derivative with respect to the first variable, df over dx1. You know, it depends on 3 variables, so you can take the derivative with respect to the first one. Then take the derivative with respect to the second variable, and then up to derivative of f up to the n variable, and you put these n functions on a vector. Derivative, first variable, second variable, up to the n, m. In fact, it's m variable. This is called the gradient. And then what I do, I take v1, the first, v is a vector, so v has also n components. You have a v1, v2, up to vm. And you take v1 times this guy plus v2 times this guy plus blah, 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 vm times this guy. These are functions, so I evaluate this function at one point. So this line is equal to this one. Question, this is a definition. Does it satisfy the 2 conditions? Yes, you know if you write f plus beta times g, look, derivative is something linear, so you are going to satisfy this condition. You just take property of derivative, it satisfies a good property, you get linearity. What about this? When you take the derivative of a product, this is Leibniz, derivative of the first one times the second one plus derivative of the second one times the first one, you get exactly this, right? So what does it mean? It means with my simple V, I've been able to construct a XP which satisfies this. Is it a problem if V is 0? What's the problem? Everything is trivial, but no, everything is 0. No, I don't have to assume V different from 0. Probably I cannot call this the derivative in the direction of V if V is equal to 0. So probably this name is not correct if V is 0, but the properties are correct. Okay, so it means this V, so it means, so I should write a sentence. One check, one easy, and this is a first year exercise. First year exercise. Because what you need is only to apply the rules. You don't have to think. You apply the rules and you check that the rules give you what you want. It's really mechanical exercise. First year exercise, check that XP defined here, I mean, the one I have defined here, satisfy condition 1 and 2 of the previous definition. Now there is a second exercise for more advanced students. Be careful, you are more advanced student. Exercise for YAM. Show that all tangent vectors, they are defined there, tangent vectors are of this type. So what do I mean? That you can all get from a certain vector of this type, which shows, if you show this exercise on this one, it means all tangent vectors can be written in terms of one V in R, or of all V in Rm. Is it clear for everybody, these two statements? They are not equivalent. One is to show that this guy defines or satisfies the two conditions. The second one is to show that whenever you have a tangent vector, it can be represented by something of this type. So once you have these two things, this implies that Tp of Rm can be identified with Rm. Why? Because for any V, you get a tangent vector. For any tangent vector, you associate a V. Tangent vector in the sense I've given. Okay. And now there is one thing which the first time you see is quite disturbing. We have a, so it means that Tp of Rm, we know it's a vector space. It was already there. Now we know that it's an m-dimensional vector space because it's in bijection with Rm. There is a basis. How should I call this basis? There is a standard notation which I need to give. A basis. And you can guess. Look, what do you have here? You have linear combinations of types of this guy, of types or of elements of this type. So in a sense, this is a basis. So basis of Tp of Rm is given by the set of d over dx1 evaluated at P, d over dx2 evaluated at P, d over dxm evaluated at P. I know the first time you see it, it looks very, very strange. This is a basis of the space Tp of Rm. Yes. No. Okay. Oh yeah, a basis, a linear algebra. You are right. Yeah, we have simply because look, any element of this is a linear combination of elements. So now if you eliminate the F, because you want it to be independent, we want it to be independent of F, you really have a basis of, or all elements can be written as linear combination of these kind of things.
Function applied to.
Yeah, you apply this to a function, but look, the definition, it coincides with a tangent vector is a map taking a function and sending it to a number. You take the derivative of this function, you evaluate at P, you have a number.
It's the equivalent classes of functions. So we don't have to.
Yeah, but they could, you're right, but now you can feel why I was dealing with equivalence class, because the only thing which matters is in fact the derivative of the function at P. But in order to define the derivative of a function, you cannot just keep the value at P. You need to know a little bit more what is around P. That's why you identify functions as soon as they are equal on a neighborhood of P, you can identify them, because what is away from this doesn't matter, but yeah, everything is coherent. So I let you think about it. So we have everything. This Tp of Rm can be identified with Rm. So it means in particular that it is m-dimensional. It's m-dimensional. And we have a basis given by this thing. I know you really need to read this couple of times before you get convinced that it's meaningful. And of course, then there is an exercise which says, if you take a parametric surface of calculus 2, you need to be able to identify my definition here of a tangent space with what you have defined with umbrella. But it's a special case because I want to have a definition which is intrinsic. Okay, so now we have M, and let's say we have Rm. And a point P, and okay, no, let me take a general situation first. Another manifold N. Remember, we know what is a map from a smooth manifold to a smooth manifold. Now, in the special case, if I take Rm here, I've defined what is the tangent space at one point. This is what we have just seen. We have a basis. So I would like to, on an arbitrary space here, I don't have a basis. I have defined the tangent space, but I don't have a basis. I've defined a basis of the tangent space in this case. So what I would like to do, I will not be able to do it today, but I would like to use the information that I know on Rm and the basis of the tangent space here to put it here. I want to get, I know already, I have a definition for the tangent space, but I don't have a basis. So I would like to use the basis of this tangent space, which I know, to put it back. So I need to define something in order to go from in both directions. So it's, again, it's a first year exercise because you don't have to think, you just have to apply the rules. But let's say it's for the second year. For the second year, you are going to check what I'm going to define. It's a bit abstract, but once you okay, you can do it. So we consider this situation M, a second manifold N, and a smooth. We have defined all these things last week. So I define two new maps, F star with upper star. Be careful. It's C infinity of, where is f of p? This is f of p. C infinity of f of p to C infinity of p. F star on F is F composed with F. And where is F? It's in this space. For any F inside C infinity of. It's a definition. I take a function defined here on the neighborhood of this point, and I'm bringing it to this point. How do I do it? Let's check composition. Take a point, take something around P, you send it to here, and F is defined on a small neighborhood. So just check it's meaningful. Composition of two functions. A first function, capital F, and then this small function F defined here. And the second one, be careful, it's with a lower star from TPM to TP, no, to TF of P of N and I need to give you F star of XP evaluated on the F is its definition XP. You should have a headache now, because if you really try to understand this, it's not completely easy. But if you work a bit on it, you will see that it makes sense. And here, XP is an element of TP of M. So what is the second definition? Now, I want to take a tangent vector with the definition I gave here and send it to a tangent vector here. And how I do it, so I define this map applied to a tangent vector. Now, a tangent vector is something which takes a function, so I need to evaluate on a function. And let's check that it has a meaning. This function is the same f, was defined here. No, the function was defined here. Then by f star, upper star, it becomes a function defined here. And now I can apply xp. I get a number. So the right-hand side is well defined. And I give this as a definition for the left-hand side. Now, what is the exercise for second? Oh, there is still something in the theorem. Do you have any question about this definition? You really need to be careful. I define a set of rules. Definition F star is a homomorphism. So I will homomorphism of algebra. Why? What means homomorphism? It means preserve the structure. So what does it mean? It means in this particular case, F star of F plus G is F star of F plus F star of G, and F star of a product Fg is F star of F star of G. It preserves the structure. This is the structure before applying F star. This is the same structure after applying F star. You need to check with the definition. This is still easy one. So it's a homomorph. And why of algebra? Because I told you this is an algebra. You can multiply and you can add elements. And I want to check that it takes something here and send it with the same properties here. Then second part of the statement, F star, can you guess the second statement? Is this was a vector space. You have an addition here. So you want to keep the structure of addition here of vector space and send it here. So it's a homomorphism of vector space. And what do I need? What do I mean by this? It means F star of xp plus yp is F star of xp plus F star of yp. And also F star of c times xp is cf star of xp. So it preserves the structure. Okay, and still in this statement, if now you have a third one, F, and then a third manifold with a map G, and if this is H it is first F and then G. So we have now 3 manifolds and 2 maps between them. Then H upper star is F star composed with G star. Observe that I have reversed the order. H star is F star composed with G. Wait, no, this is not correct. Wait a second. No, the second one is not correct. It is G star composed with F star. Again, this is what I call the routine theorem or routine proof. You don't really have to think too much. You don't need any new idea. Routine proof. You don't need new idea. You just use the definitions very, very carefully, and you check that if you go step by step, it's correct. You don't need to think about something special. You apply the definitions. Any question? Yes. This one? This one? Wait. So this one? This is just a composition of 2 functions. You always, so you apply F and R. No. Wait, small f is a function defined here. So you first apply this and then this function f. So this is correct. You always start, you apply first this one and then this one. Always. There was another question, yeah? Why do you want to take infinitely many? Isn't it complicated enough? Please do it with 3, this is enough. I don't know what happens if you take infinitely many. No idea. Maybe we have an expert who knows, but I'm not even sure that it's well defined taking infinitely many. Yes. Check this theorem. Check that it preserves the structure of algebra. You are not second year, but check that it preserves the structure of algebra of this and this. Check that the second one preserves, this is a vector space, so it sends the properties of a vector space to the properties of a vector space. And then check, again, it's just applying the definition that if you have 2 compositions, they respect this. This is, but again, you just have to follow the definition carefully. Sorry? Second year in Nagoya. Maybe you're second year student, you're new pace. But what in your home university? Okay, so you are a 5th year or 6th year here. Okay, second year or undergraduate. Second year of undergraduate. Okay. I will keep some exercise for master students. Okay. I will not be able to do it, but now what can we do with this? Forget the third one for a second. Suppose that this is our M. Now look, maybe I just need to say one remark and then I will finish. One remark. If it's from, no, this is too easy. If F from M to N is a diffeomorphism. You remember diffeomorphism means it's bijective diffeomorphism. So it means it's bijective and the inverse has also good properties. So if F is a diffeomorphism, then F minus 1 star is also a homomorphism. So it means you can have the same properties, homomorphism. Homomorphism. So you have the same properties for the inverse, and it implies, or we say that F star is a isomorphism. Isomorphism. This is just one more word. It just means that not only F star is a homomorphism, but also its inverse is a homomorphism, and we call this an isomorphism. And the proof is rather easy to check that the inverse is also a homomorphism once you use these compositions. So what I want to do next week, or in 2 weeks' time, we have on this space a basis for the tangent space. At every point, we have defined the tangent space, and we have a basis. Look, now I can use this F lower star inverse. I will use the inverse to bring this the basis on Rm back to this space. So I will have a basis on the tangent space here, thanks to the basis we have shown on Rm. This is the next step. So I get the tangent space is defined without any basis, but for Rm, we found a basis, a natural basis, and I'm going to bring it back to this space. Okay, so in 2 weeks' time, we work on this, and then we are dealing with vector fields. So I encourage you to read more than once what we have done today, but you will see if you just read and try to figure out what we have done, it's not so complicated. We just follow some definitions. Okay, thank you, and see you in 2 weeks' time.